So welcome to the award session. And actually I have to tell you that chairing the award session is maybe the best session that you can chair, because you will meet only happy people. And actually we have some awards, and the awards that we have is Best Paper Award. And we selected this paper together with all the program committee. And then we have Best Reviewer Award, that is a bit more tricky because the program committee only see parts, and then we define clear rules. And we'll see in the future, the idea is also trying to make public all these rules and to have transparency. And then for the Best Young Researcher Forum Award, Christian Berger will help me. I think he's here around. Ah, very good. Because Christian was one of the co-chair of the Young Research Forum track. And then the other session will be managed by Ivica, that is both general chair and head of the steering committee together with Philip Crookton. And then I will manage that. So, but probably we can start. I don't know if you have any question, otherwise we go ahead. So, Best Paper Award. The first one is going to understand the software vulnerabilities related to architectural security tactics and empirical investigation of Chromium, PHP, and Thunderbird. I don't want to read all the authors, there are too many. Do we have some of these authors here in the room? Ah, too easy, guys. So, do you want to come? Should I stay here? Thanks. So I'm using microphone not because I want to feel a star, but because we are streaming. And actually this means also that for the Young Research Forum there will be a presentation, and then we will ask you also, the presenter, to use the microphone, and the same for the Most Influential Paper Award. But let's go to the other Best Paper Award, that is Continuous Analysis of Collaborative Design. And do you have the authors here? Somebody? Yeah. Okay, we can go to Best Reviewer Awards, and we have two also. So the first one is Lars Grunske. That is here also. And the second one is Matthias Galster. Yeah, you got two. So now is the turn for the Young Research Forum.
Yeah, thank you very much, Patrizio. Oh, here's a... Good. The Young Researchers Forum this year was a very great day on Tuesday, if I'm not mistaken. We had very great discussions, presentations, and a nice panel discussion also. And we had very many great submissions also to this forum, and it was not an easy job to select the Young Research Forum Best Paper Award. This year we are very happy to present it to Susanne Braun. I hope you're here. You're wonderful. So, and we also have a presentation now, right, Patrizio?
Yeah.
I'm not sure. Yeah, thank you very much for this award. Now I am going to really briefly present what I am going to do in my PhD. Now what I do, I am dealing with optimistic data replication. And why do I do that? Because it is an important enabling technology for high availability and scalability. Now it's important to note that only the optimistic approaches will give you high scalability. And what does that mean? Optimistic replication in this context basically means that the replicas do exchange updates asynchronously. And this means that you can have inconsistencies between your replicas, and also you might observe write conflicts. And if you want to avoid severe concurrency anomalies like lost updates, you will have to have some means of proper conflict detection and resolution. And basically you are dealing with the complex task of concurrency control in a distributed system. Now, we detected that this is really challenging in practice when we did that industry project together with John Deere. And we were developing an ecosystem of mobile applications for smart farming. And those applications were operating on shared data and had to be fully offline capable. And for that, we required optimistic data replication in order to realize that. Now, what is the problem with state-of-the-practice optimistic data replication? The thing is that it runs on a very low level, on a very low semantic level, close to the database management system. Often it is even incorporated into the database management system. And the problem is that all the high-level semantics of your business applications are not available on this low level. So they have to apply syntactic techniques for conflict detection and conflict resolution. And this leads in practice to the following issues. Now, first, you very often are not able to properly resolve the conflicts, and this ultimately results in lost updates. Second, there might be conflicts that you even cannot detect with pure syntactic technologies. You have to incorporate application semantics for that. This often results in constraint violations. And third, there might even be conflicts that you detect syntactically, but they are actually not conflicting on the semantic level. And if you want to avoid all of these issues, you will have to apply error-prone workarounds, which will result in a drastic increase of the complexity of your application. And it will also very negatively impact maintainability of the application. And now what I do, I believe that all of these issues could be drastically mitigated if the internal concepts and workings of optimistic data replication were rather driven by semantic than only by syntactic properties. And the basic idea is we want to exploit application semantics in order to develop methods, best practices, and concepts so that you can design your high-level business operations for maximum compatibility and in order to minimize the write conflicts. And second, we want to have better support for semantic reconciliation. And third, I want to provide a technical framework that enables software architects and developers to implement a custom solution for optimistic data replication that is able or that can exploit application semantics. Now, the technical framework, it is a combination of domain-driven design and model-driven development, as well as operation-based optimistic replication. I will provide the developers and architects with a textual language with which they can not only specify the domain model, but also specify the compatibility of the high-level business operations and the conflict relationships. By that, we can exploit the high-level business semantics during conflict detection and resolution. And out of that model, we can generate a lot of things already. For example, we can generate the complete persistence layer. And on top of that persistence layer, the services of the applications can run with the high-level business operations. Of course, the operations will still have to be implemented by the developers. But we can also generate some clue code that will bind at runtime to our library. And this clue code, for example, takes care of logging the high-level business operation so that we can use that information during conflict detection and resolution. And the runtime library will take care of implementing the other concepts of optimistic data replication, like, for example, update propagation, update ordering, reconciliation, and consensus. So this is basically what I'm working on. So one last word. I believe that this topic is becoming increasingly important, and also that optimistic data replication is inherent to microservice architectures, for example. So that's it. Thank you very much again for this award, and if you have any questions or are interested in my work, just write me an email.
Yes, and finally we have the most influential paper award. So not about what people will do, but what people have been done and influenced many people. And we have looked from 10,000 years, not 10,000 years ago, but 10 years. But at that time, you know, there was no ICSA, but there were like 3 conferences, ICSA, and then as a part of Comparch, CBSE, and COSA. So we looked at these 3 venues. And the decision was relatively easy to do because it's based on some quantitative data, and that's citation index. But we had a team, Patrizio and Maria as program chairs, and then Philippe Kruchten and Ralph Reusner, Jan Gorton, Ipek Zaika, and me have been. And we have found that there was one paper who was the best, and that's, or people which were the best, and that's Vittorio Cortalese, Vincenzo Grassi. They are here, and so they can read the title of the paper also. But congratulations. It's really a pleasure to give you this. Yeah, you have 2. Yeah. Also privileged to listen to.
Okay. Thank you, Ivica, for the introduction, and it's really a pleasure for us to stay here and for this award. It was really a wonderful surprise for us to receive it, and also quite unexpected, because, of course, when we wrote this paper, we didn't think we were writing an influential paper. We are just trying to write a good enough paper and to have fun doing that. But anyway, apart from the pleasure, another nice thing about receiving this award has been that it has been the occasion for us to rethink about what we did in these last 10 years, which is always a useful exercise. Sometimes it could also be dangerous anyway. But apart from us, it was for us the occasion for rethink about the evolution of the field covered by our paper. This architecture-based dependability analysis of software systems. So this will be the subject of our brief talk, how this field has evolved. So, of course, without going too far in the past, and we don't no claim that we will be able to predict exactly what will happen in the future, we will focus on a much shorter period from more or less the time we started thinking about our paper up to now. Since I'm older than Vittorio, I will talk about the past, and then he will talk about more recent times. But there is a difference. Anyway, so which was the state of the art at the beginning of this period? From a conceptual viewpoint, there was this well-established conceptual model about the failure pathology of the system. The last paper where this model was presented was published, as you can see, in 2004, but the elaboration of this model started almost 20 years before with a paper by Jean-Claude Laprie. Then this model was refined and elaborated by Laprie himself and other researchers like Randall, Vizenis, and others. So the basic element, among the basic elements of main elements of this model, there was the idea that a failure is a deviation from the intended behavior of a system. The ultimate cause of a failure is a fault that occurs in the system. It could be an internal fault. For instance, think of some bug in the code which is activated during execution. Could be some external fault, for instance, not to arrange input parameters. But for a fault to become to lead to a failure, it must first generate an internal error in the system, where an error is a wrong variation in the internal state of some component. And then for an error to become a failure, this error must propagate up to the component interface and then up to the system interface to lead to a system failure. And if during this propagation path, this error is this propagation path within a component, then from component to component through their connectors, if this error is for some reason, some way masked during the propagation, it actually will not lead to any failure of the system. So this was a very well established, very well understood conceptual model, which was the state of art from the viewpoint of dependability analysis of software systems. Well, it lagged well behind this model. There was this initial paper by Cheung published in 1980, which was based on a much simpler model. In a sense, it was based on assumption. It was a stochastic architecture-based model for reliability analysis. It was based on the simple assumption that when a fault occurs, it immediately leads to a component into a system failure. No idea of propagation path, no idea that this error could actually be masked during this propagation. In a sense, this model was justified in this assumption because it was published some years before the presentation of the failure pathology model. But after that, there was, to the best of our knowledge, almost no evolution in the assumption that were adopted. So the state of art, more or less at the time we started thinking about our paper, can be well summarized by this excerpt from one of the last papers published before ours. The failure model component, software components, was still can be still described in this simple way: two-state model where the occurrence of fault immediately leads to a failure of the component and of the system. No idea of propagation path. There was in those years some, within the software community, some initial attention given to the concept of error propagation. There were some papers published about this topic, but they were not well connected, integrated with the general field of dependability analysis. So our, in a sense, quite simple idea was to try to fill this gap between what was clear from a conceptual viewpoint and the actual practice of dependability analysis. What we tried to do was to embed within our model this idea that there is a propagation path for a fault, for an error within a system, and that during this propagation path, this error could actually be stopped in its propagation before reaching the system interface. And in that case, it will not lead, according to the conceptual model, it will not lead to any failure. So we wanted to model not only the failure characteristics of each component, but also the idea that there can be different propagation paths within a system, and we should model this, and the ability of each component in masking rather than propagating some error. And so we embedded these concepts within our model by introducing in particular this idea of error propagation probability, which was intended just to represent, to express this kind of information, the fact that some component would actually stop the propagation of some error within the system. And once we introduced this new element in our modeling approach, the remaining part of our work, in a sense, was just a matter of mathematics. This is just a taste of the mathematics we used. We were able to derive closed form matrix expressions for the evaluation of the reliability of component-based systems. And once we got this closed form expression, we could differentiate them to carry out sensitivity analysis. And from sensitivity analysis, we could identify critical and non-critical components, where critical components are those components where, at least for some range of the possible values, small variations in the value of some parameter describing the properties of some components can lead to huge variations in the overall sensitivity. So this was, in a sense, our contribution, and then Vittorio, the young.
Dear Grandpa, can you hear me? Yeah. Yeah, so, I mean, the nice surprise was that actually the model was working, and especially in some areas, I mean, in some ranges, the parameters were sensitive to the, I mean, the system reliability was sensitive to the parameters. What happened right after? What happened right after is that Vincenzo discovered that I was not working very well, and in fact, he collaborated with other authors, very fruitful, and yes, they published right after, I think 1 year, yeah, few years later, 3 years later, they have published this paper that was extending the model to other failure mode, because we only considered, I mean, failures due to local values of variable, and they extended to timing failure and other types. So they have built this framework that could include a different type of a failure mode for single components. This contribution, we retrieved this type of contribution even very recently. This is a paper from COSA last year, Quality of Software Architecture, this conference last year, and the same concept is reproduced here. This figure is important because you see, when you increase, I mean, the type of failure that you can incur in a component, it's good because you are going in more accuracy, right, for your model. But as opposite, if you observe this is quite simple model as an internal model of a component, what you see is that there are more parameters, no? More parameters to be modeled. You mean probability of going, I mean, of failing in different modes, probability of recovering from different modes. So there is a clear trade-off between the accuracy of the model that you can introduce and the problem of using that models, no? And in fact, it was very useful to go through the recent literature to discover that the next, I mean, papers after ours were trying, I mean, the main directions for us that we identified, they look only different, but they are not different at all, because they try to address this problem of estimating parameters and try to make these models usable. One category of contributions that we have identified is all the work that has been done in terms of online systems and runtime analysis, because this is actually, I mean, we have listed papers, I mean, presentation today as well. I mean, because this is, of course, self-adaptive system, evolving system. This is the domain, I mean, the paradigm that is very interesting to be studied. Then there are contributions from several authors in this area. Basically, I mean, some of them, they are based on model checking, and they address problem of reliability of these systems. Another contribution that I mean, we identified is about uncertainty, which goes more or less in the same direction. I mean, because, you know, we deal with system that evolves. We deal with system that have, part of them, they are uncertain in terms of parameters, in terms of behavior. So addressing uncertainties is something that has been made in the recent years in this area. And another one, which is very interesting as well, is about collaborative approaches and web service-based approaches. Like, for example, there is this paper from Yan Liu about the perception that users have about the reliability of systems, depending on where they are located in the world, so depending on their connections. So several authors, actually there are many papers from Lars. I didn't know Lars got another award today, otherwise I was cutting them, I mean, from my slide. But in any case, I mean, yeah, I have to recognize that Lars contributed a lot to this field. I mean, yeah, so we have. And that were the main directions. So we have a figure that we are in Sweden, there are forests, so we wanted to represent forest. Actually, we had only one tree today, but then Vincenzo decided that we need forest because it was too ambitious to have only one tree. Our message is that only on deep roots, like the conceptual model of fault, error, and failure, and the Tune model, that they go deeply in the past, as Vincenzo has shown, you can build a firm body that can stand on those roots, and this firm body hopefully can generate multiple boats that are, I mean, the future. So, of course, this tree, I mean, the tree with our body is not the only one. That's why we added other ones in the forest. We can collect these directions, as I said, about the trade-off between usability and accuracy, and we think that this direction was the most interesting one. Now, what about tomorrow? Just one slide about tomorrow, because I mean, we want also to give. It is lunchtime, eh? One slide. One slide about tomorrow. There are many possible directions. One direction that we found interesting is about round-trip software dependability engineering. In general, for people working on model-driven engineering applied to non-functional analysis, there is one direction that is very well assessed, which is the forward path. We have a lot of approaches that can generate from software models, can generate non-functional models, no? Reliability, performance, and so on. So that's something quite well assessed. In the last 10-15 years, there have been a lot of contributions in this direction. What is still not very well investigated is to make this software dependability engineering process like a round-trip process. So the way back, the backward path. I mean, once you have these indexes here, you have probability distribution, function variance, average, and numbers. And those numbers are difficult to be interpreted and to give some feedback to software engineers. So we think, that there is a lot of work to do in this direction in order to make automated approaches that can, for example, support the interpretation of indices and to give feedback in order to solve problems in the software models of designer. That's only one idea. There are other, possibilities. And that's all. Two final considerations. A good consideration. We remember that this paper was rejected 2 times before CBSE with, another 2 conferences that we don't name here. And then, we don't want to name, of course. It's only syntactical, non-semantics. And then we got 3 A's at CBSE. So we were, at the end, we were very proud. 10 years ago, actually, this paper was very cited. So especially to young researchers, don't give up. When you have your own research in your hand, don't give up. There could be some success later on. This is a good one. A bad one is what happened to us in the last 10 years, and that's what happened. Actually, Vincenzo was already old at that time, so didn't change too much. But to me, it has been very tough to understand this. So this is an excellent reason for never writing a most influential paper. That's it. Thank you to the committee and to all of you. Thank you.
We have lunch. Good news. The best performance.